Today we are going to study the intermediate representation, or IR, that is sitting between the C or C++, that is higher level language, and assembly, that is the low level language. So recall that the purpose of this IR is easier to perform optimizations. C is too high level, so it is difficult to perform optimizations, and also assembly is too low level. It is also difficult to apply optimizations. IR is meant to be the sweet spot between C and assembly that is easier to perform optimizations. So the KECC IR is inspired by LLVM IR because it is one of the most widely used compiler infrastructure, and it is quite well designed. So I just adopted many design choices of LLVM to KECC for educational purposes. So I think there are four main ideas. Here are the control flow graphs, registers, and unambiguous variable names, and explicitly annotated types. You can think of this slide as the summary of the IR's characteristics, and we are going to look into each of them one by one. So first characteristic of this IR is control flow graph, or CFG, that is looking like this. This is just a graph instead of many lines of code. So in C and C++, you're going to write programs in line by line. For example, in this line, it is going to store 100 to a variable that is called ACC, the shorthand notation for accumulation variable. And in this for loop, it is going to loop for 100 times, and it is adding this I to ACC. And after this loop, it is going to return the accumulated value. So the C and C++ program is written in this way, in statements. And there can be some nested statements inside this composite statement. For loop in this example is a composite because it is containing another statement. On the other hand, this is just a single statement. It is on its own a statement, and it doesn't have any inner statement. This is good to understand the program. It is the most familiar form of program that is most accessible to the programmers. But for translation purposes or optimization purposes, we are going to translate this program into this program in the right. So it reads like this. At the beginning of the program, you're going to get into this first block. And in this first block, ACC, a variable, is assigned 100, and I is assigned 0. And it is going to flow to the next block. And in this block, it is comparing I and 100 and putting this variable into this variable that is called a cond. And depending on the value of cond, it goes to this block or this block. If the condition is true, that means I is less than 100, and it is going to the next block here. And it is accumulating the I here, and it is incrementing I to the next iteration and go back to the condition here. On the other hand, if the condition is not met, that means this for loop is over. So you are going to jump to the last block that is returning ACC to the caller of this function. So you can now see that these two programs are meaning the same thing. It is calculating the summation from 0 to 100, and it is returning the summation. But in the left program, which is looking like C or C++ program, the program is consisting of statements, but on the other end, on the right, the program is consisting of blocks and edges like this. So in this representation, these rectangles are usually called blocks or instruction blocks or basic blocks. So let's say that it is just a block. And there's an edge between the blocks. For example, after executing this block, you are going to jump to this block. So we are going to say this is jump. But others say this is branches or continuations, blah, blah, but we are going to say just it's jump. And furthermore, in order to express the idea of comparison and breakout, in this statement, we are going to represent this idea with conditional jump. If this condition is true, you are going to jump to here in the next block. And on the other end, if the condition is false, you are going to jump to the last block, returning ACC. So depending on the value, you are going to jump here or here. So that is the reason why it is called conditional jump. So these blue ones are the ordinary jumps, normal jumps, and these red ones are conditional jumps. Now the next question is, why do we do this? Why do we translate a statement-based program into a control flow graph-based program? The main reason is simplicity. So this CFG has much simpler structure than C and C++ statement because it doesn't have any nested level of statements, and also it doesn't have any exceptions on the control flow. So for example, in C and C++, in a for loop, you can break out or you can continue to the next iteration. So it is a little bit irregular control flow. Depending on the enclosing for or while statement, you're going to go to the first iteration, first line of the loop, or you're going to just break out the loop and go to the line right after the loop or so. So it is a little bit exceptional. But in CFG, you don't need to deal with such things. So everything is represented as a graph, and you can just compare some comparison condition here, and depending on the value of the condition, you can go to anywhere in the program. So it is a little bit more simple in structure. So these two things are explained. So thanks to the simplicity of CFG, it is usually used in compilers between C and assembly. So this CFG representation is much more similar to the program structure of assembly, where everything is just flat. There are a bunch of just instructions, and you jump to the line number instead of equalizing the structure in the assembly. So, but statement has a very rich structure of the statement. So it is really difficult to translate the C-based C programs into assembly in one step. That's the reason why we use an IR that is based on CFG. That is easy to translate from the statement-based languages, and also it is easy to translate to assembly languages. Furthermore, it is easier to implement optimizations on this CFG because, as we said, the program has an explicit notion of blocks and jumps, etc., in the graph representation. So we can reason about the control flow of this program more easily. And therefore, we can easily implement optimizations based on this CFG representation. So these two, necessary for translating to assembly and easier to implement optimizations, are the two reasons why we prefer IR over C-based, statement-based C languages or assembly, the flat assembly languages for the purpose of optimizations. Okay, now let's turn to the second characteristics of this IR language, that is registers. So this IR is usually called register machine because all computations like arithmetic operations such as plus, minus, or division or multiplications are performed on registers instead of directly on memory. So you have to, if you want to operate on some values that is stored in memory, then you first have to load this value into registers and perform your operation, for example, add A to B, and then store it back to the memory. So you cannot directly work on or directly compute the values in the memory. That's the meaning of this register machine. So for example, in C and C++, you may want to write like this: x equals A plus B. That is, you're going to read these variables A and B, and then compute the addition, and then writing the value to this another variable x. It is fine in C and C++ statement, but in IR and assembly, it is usually written like this. You first load, explicitly load the value of A into a register. And furthermore, you also explicitly load the value of B into a register instead of directly adding values A and B here like this. And after loading the values into registers, and you're going to perform the computation and get the result X here. Then you're going to store it back to the variable X that is stored in the memory. So that is the translation of this one-line segment into an IR. Now you may think that this IR representation is consisting of 4 lines instead of just 1 line as in C and C++. So why do we do this? Why do we expand this 1-line code into 4 lines? Because that is much easier to reason about and perform optimizations. So it is a very important point of this register machine, and we are going to discuss it in our later slides with examples. Let's first look at an example translation regarding these registers. So here is the familiar example from the last slide, that is getting the summation from 0 to 100. And because IR is CFG, we are going to translate this program into this program, as we discussed in the previous slide. But actually, we need to perform one more level of translation from this to this. That is replacing these memory variables with these registers. So here, instead of writing 100 to a memory that is stored in that is a variable ACC, it is going to write 100 to the register that is named ACC. So let's say that this ampersand is marking the fact that this is a register. And it is also writing 0 to I, and in the next block it is performing the same things but with the registers instead of memory locations. That is the only difference between these two graphs, basically. So in IR, we prefer such form to this form because the IR allows computations only for registers but not for memory values. So we need to transform in IRgen and later optimization passes. We're going to translate this program written in memory into this program that is writing and reading to registers. Okay, so far so good. But what's the benefit of these registers? Why do we need to convert these memory locations into registers? Because the only difference we can see from these two programs is the names. We are just prepending the variable names with ampersand. What is the difference? Why we do this? The reason is that register guarantees, by definition or by the properties of the language, it guarantees that the register variables are not interfered with any other part of the program. So here's an example. Okay, let's say that this var is a memory value, and each address is taken, and it is sent to the function foo. And after returning from this function, we cannot assert that var should be 42. Because this function foo may change the content of var. Maybe it can change var to 666. That is very different from 42. So this assertion may fail because of the interference from the function foo. And here is another example in which this global variable may affect the execution of this program and may change the value of this var. This var, its address is taken and it is stored in the global variable. And maybe it is possible that maybe a concurrent thread may read the pointer of this global variable and writing another value, for example, 17 to this variable. So as a result, in this assertion, it is not possible to assert that the var should be 42. As explained in the previously, maybe another thread may store value to this G. That is a var. So, and there are many other possibilities of interferences of other part of the programs via this function call, via this global variables, etc., etc., etc. So that's the reason why it is more difficult to perform optimizations on memory values. because of the possibility of the interferences of other parts. On the other hand, register values is by definition not interfered by the other part of the program. The main reason is that we cannot take the address of this register variables. It is impossible to get the pointer of register value and give it to other entities. So because it is forbidden by the language. That's the reason why you cannot do this. And as a result, if $var, register var is assigned 42, it should be 42 here in assertion. It should be always true because of the impossibility of interferences of other parts of the program. So that's the difference. Possibility of not interferences. That's the reason why register values are much easier to implement optimizations. So for example, in the above two programs, we really cannot perform constant propagation. Even though var is 42 here, we cannot constant propagate this var 42 to this var because of the possibility of interferences of the previous lines. But here, it is very easy to do so. $var should be 42, and it should continue to be 42 after any lines of code. If I'm not writing a value to these registers. No other part of the program cannot interfere with the value of this $var. So we can easily replace reading this register, read value of this register with 42. And in turn, we can completely remove this assertion in the program, in the optimizations. Now let's turn to the third characteristic of this IR, that is unambiguous variable names. That means variable names are ambiguous in other programs, other forms of programs. For example, in this C program or pseudocode in the left side of the slide, I is ambiguous here because I is defined or declared twice. Here, I is given 42, and it should be 42 at this line. But at this line, I is one more time declared here. So it is going to get assigned 0, and at the end of this iteration, it should be 100. But after this iteration, it is crucial that this I declaration in this for statement is gone. You can no longer access this variable I that was declared in for loop. And after this line, the original I that was assigned 42 is restored, and at this line, I should be 42. So it is actually, this is a pseudocode, but this kind of reasoning is actually happening all the times in C and C++ programs. A variable of the same name can coexist, and after, so this is the original one, and it can be hidden by a new one, and after new one is destructed, the original one should be restored. So in order to support such a case, we need to disambiguate the variable names. Oh, this I in the assertion should really point to the variable that was declared here. It is not declared in this for loop. We need to disambiguate or resolve the name, depending on the position of the statement in the program. So this is the job of this IR generator. And in IR, we need to distinguish this I variable into two things. Let's say it is I0 and I1. And here, I0 is assigned 42 because it is meant to be corresponding to the original variable I. And we assign 0 to I1 because I1 is meant to be the variable that was declared in this for loop. And we use I1 in these iterations because here in the iterations, I is really pointing to the variable that was declared in this for loop. And after this for loop is over, we are going to assert on the value of this I, and in this case, this I should be I0 because this I should be pointing to the original value I here. So this IRgen is basically disambiguating the ambiguous names of I into I0 and I1 when we need to implement such a name resolution function in IRgen. So the key idea of name resolution is maintaining a mapping from name to variable during the translation. For example, when we are translating a statement in this for loop, we know that I should point to this. But after this for loop is over, I should point to this. So when you're translating this program, statement-based program, you are actively maintaining the variable mapping. Oh, I should be pointing to this variable, or I should be pointing to this original variable here, blah, blah. So you are actively maintaining this mapping, and using this mapping, you're going to rename the occurrences of this I into I1 or I0 correspondingly. So this procedure is historically called semantic analysis or symbolic table lookup, but we are going to use the variable name resolution because I think it better reflects the nature of the computation that is done here. So we are going to visit this topic later when we discuss IRgen more deeply. And here is another topic that is worth noting, that is dynamic scoping versus static scoping. So in C program, when you're going to mention I, the meaning of this I or the variable that this name actually point to is defined solely depending on the structure of this program. Oh, I is declared here, and it is let's say it is the nearest declaration of this I. So this I in assertion should resolve to the declaration in here. The reason why it doesn't resolve to this I is that it is in the nested block, and its effect, the declaration of this for loop's I's effect, is over at the same time that this for loop is ended. But in some other kinds of languages, you cannot reason about the variable name resolution in such a way. For example, in JavaScript, the meaning of this variable I depends on the execution. For example, when you call a function foo from this context, this I should resolve to some global variable. Or if you call a function foo from another context, this I may resolve to the variable that was declared in the caller. So the execution context or the call stack may change the meaning of the variable name I. So that is usually called dynamic scoping instead of static scoping. So here's the definition. In dynamic scoping, the name resolution depends on the execution, like call stack. On the other end, in static scoping, name resolution depends solely on the abstract syntax tree, like in C. So JavaScript or even Python is dynamic scoping in some sense, and C and C++ and C# and many compile languages are static scoping. I usually prefer static scoping much to the dynamic scoping because dynamic scoping is very not modular. Renaming variables within a module may change the semantics of the other modules. It is very difficult to reason about the effect of name changes to in the global systems. On the other end, in C and C++, we are using static scoping. So if you consistently rename a variable within a module or within a function or within a class or struct, then its effect is limited to the module, and it doesn't affect the semantics of the other modules. So it is much modular. That's the reason why I prefer static scoping, because this modularity is very beneficial for building a large-scale software. And unfortunately, we are going to deal with C and C++, that is using static scoping. So we are going to implement variable name resolution for static scoped languages. The first characteristic of the IR is the explicitly annotated types. On the other end, C doesn't explicitly annotate types always. Let's see this example, 42 plus 0.42f, which is not explicitly annotated with types. This 42 should really be an integer, and this 0.42f should really be a float. And as a result, this expression's meaning is that let's convert this integer into a float by casting integer value to a float, and then adding these two float values here. But it is not explicitly annotated, so we need to discover this type information in the IR. The reason we need to discover this information is that it is very naturally necessary to generate assemblies because we need to select the instructions depending on the types. So for example, the meaning of this plus, A equals B plus C, depends heavily on the types of B and C. If B and C are integers, then it is just addition in integers. And if it is an integer and float, then as I said, we first need to convert this integer variable into a float, and then add the two float values into the summation. So we need to select different instructions in assembly for this case, integer plus integer case, and integer plus float case, and other cases as well. So that's the reason why we need to explicitly know the types of each sub-expression in compiler. So in IRgen, we guess or we infer the types of sub-expressions. Oh, this should be integer and this should be float, and we need to insert a type conversion of this 42 from integer to float and do some addition and blah blah. So this kind of thing is usually called type inference or type deduction. For your information, our IR has the same exact types with C. We have scalar types like integers and floats, and pointer types, and struct types, and array types. But for KECC, we do not support enum and other advanced structures. So these four are the things you should support in the homework. The final characteristic of this IR is static single assignment, or SSA. SSA means that a register is defined at most once in your code. So this $var equals v should appear at most once in the program. So in this example, this is disallowed because the register variable var is assigned twice. So it violates the rule of static single assignment. Therefore, it is rejected in our IR. But it is important to note that this is a static single assignment, but dynamically in the execution, it may be assigned multiple times. For example, this cond in the left bottom example here, it is written once in the program. If you look at the program, the assignment to cond is only happening once, but in the execution in a loop, you are going to assign to cond multiple times. But it is okay. We are requiring static single assignment, but not dynamic single assignment. So cond can be assigned multiple times in execution dynamically, but in the code, statically, it is assigned once. So we allow this kind of code. Okay, the reason why we deal with such a rule, static single assignment, is that it is using this SSA, it is much easier to implement optimizations. So recall that register alone simplifies the job of optimizations thanks to the automatic verification of non-interferences. If the variable is register, then it is automatically not interfering with other part of the program. But SSA enables us to reason one step further. So this variable, once written 42, is 42 forever in the later execution. It is not changed in your code, except for the case that it is going back to the loop and reassigned. So when a variable is read, then it is the same value that it was written above. So you're going to exploit this fact in the optimizations. This fact is usually called the SSA property, or it can be thought of as a non-interference from even the code itself. Between the write to the register and read from the register, regardless of whether whichever code is inserted between these two lines of the code, it doesn't matter. When you read a variable from the register, then it should be 42 always. So that's the non-interference that is offered by static single assignment. And thanks to these non-interferences, SSA makes the life of optimization developers much easier. So we are going to study SSA as well when you are going to work on the mem2reg optimization. And we are going to study these SSA algorithms and all the details of this SSA. But for now, let's not assume SSA because it is a little bit advanced topic. So let's revisit later. So to summarize, our IR has these 5 characteristics: CFG, a register, unambiguous names, explicit types, and SSA. So please, so this is just a brief introduction to the IR. And in a later slide, in a later video, we are going to look through the precise definition of IR in the KECC line by line, so that we can see what's happening about these key ideas in the actual code. So the homework is watching the next video that is describing the IR, and actually read the skeleton code's definition of IR and its interpreter, so that you can get some feeling of what's going on in the IR. It will be necessary for homework 2 that will be announced soon, that is generating IR from your C statement, IRgen.